For our project, we decided to do the analysis of a bicycle. So this bicycle is typically used in outdoor environments, varying temperatures from negative 25 degrees in the winter to 35 to 40 degrees Celsius in the summer. Its intended application is to be used for transportation around campus and around the city, and potentially for recreational use. Now, the bicycle frame has no visible corrosion. The bicycle frame is most likely made out of steel and is coated with paint as a precaution to corrosion. It acts as an inhibitor and prevents the chassis from corroding, since it provides a barrier between the steel and the moisture in the air. The top left corrosion is on a screw. Now this screw acts as a sacrificial anode for the frame. The metal chosen for the screw is most likely more anodic than the frame, so that the galvanic cell created between the two metals will cause the screw to corrode rather than the actual chassis of the bike. For this project, we will be analyzing the chassis and the bolt and trying to prevent the bolt from corroding at all in the first place in all weathers and temperatures. For the project, we have come up with a list of function requirements, design requirements, objectives, and constraints for the bike. Starting with the functional requirements. The chassis of the bike must be able to withstand tension and compression stresses exerted by the user. It must also be able to support the weight of the user. It should be able to resist corrosion in all Canadian weather conditions and all temperatures. The bolt must be able to withstand shear stress without failing, and it must be able to hold the spring of the spring to the chassis. Next, we have the design requirements. So the chassis must support a weight of 150 kilograms minimum with a safety factor of 2 or 300 kilograms, so that it is strong enough to prevent failure from any forces exerted by the user. It must also not weigh more than 10 kilograms so that it is lightweight and easy to use. For the objectives, we will be minimizing cost, since we don't want an expensive bike, minimizing mass so that it is easy to use, and we'll be maximizing the stiffness so that it doesn't bend while being used. Last, we will be constraining the size of the chassis, so the lengths of each chassis member will be fixed, and the size of the bolt will also be fixed. For our first MPI, we decided to maximize the yield strength per unit density in order to minimize mass and maximize strength. It is important to have a bike frame with a high strength so that it will not fail under the load of a human sitting on it. It should also have high strength to be able to withstand any forces while riding the bike, such as braking or dealing with bumps on the road. To represent this force, we applied a 3,000 Newton force to the seat of the bike. This is an applied force slightly stronger than the mass of a 150 kilogram human with a safety factor of 2. We wanted to ensure that the bike frame is very safe and will not deform plastically until unreasonable amounts of mass is applied. Through calculations, it was determined that the highest internal force applied to any beam was 2,639 newtons. We are also minimizing the mass. This is important because we want to make the bike as easy to ride as possible. As the bike is lighter, it requires less force and less energy from the user to travel at a given speed. This makes the ride more endurable and makes it much easier to travel around on the bike. It also requires less force to accelerate the bike. This can be seen through the equation force equals mass times acceleration. As mass decreases, acceleration increases. We chose the maximum weight of the bike to be 10 kilograms. This number was achieved by researching average weight of bikes. On CES, we decided to limit the cost of the material to be under $10 per kilogram. We also wanted the bike to be relatively inexpensive, and we felt this would be a good price to cut it off at. We also specified that the material had to be strong have that the material have to have strong weldability properties since the frame is a welded component. There's no point in picking a material that would be difficult or impossible to weld. We also wanted the material to be durable in fresh and salt water to withstand any outdoor conditions such as rain, snow, and hail. From our first MPI, our material choices ended up being martensitic steel, austenitic steel, 6061 T6 aluminum, cast magnesium, bronze, copper, and rolled lead calcium. Our second function involved the prevention of the buckling of the frame. So for our second MPI, we needed to maximize Young's modulus per unit density in order to prevent buckling and minimize mass. Since many of the frame's tubes undergo compression with an applied force, we felt it was important to ensure that none of these tubes in compression would collapse from buckling to prevent the bike from breaking and to have better safety for the user. The same applied force of 3,000 newtons was used from above. It was calculated that the highest compressive force acting on any of the tubes was 1,596 newtons. Again, it was important to minimize mass for the same reasons listed above. Cost, weldability, and durability in freshwater and saltwater were also considered for the same reasons again. From our second MPI, our material choices ended up being ferritic steel, austenitic steel, copper chromium, 6061 T6 aluminum, cast magnesium, bronze, brass, and lead. Based on these materials, we decided to go with 6061 T6 aluminum for the bike frame. Although its strength was not as high as steel, it is much lighter in mass and still has more than enough strength for the design purpose. This is the same for brass, lead, bronze, and copper materials, since they have high densities which result in very heavy bikes. Magnesium is a very good metal as well, since it is lightweight, even lighter than aluminum, and is also strong enough to prevent the chassis from having plastic deformation or buckling. However, it is a much more expensive metal than aluminum, and we felt that in this case, having an inexpensive bike is more important than making an already lightweight bike even lighter. This bike is used for transportation and not for racing, so maximizing its performance is not essential. After selecting the material for the chassis as 6061 T6 aluminum, we needed to select the material for the bolt. Now, the selection of the material for the bolt is important because we don't want to cause corrosion on either the bolt or the chassis, and it needs to be strong enough to support all the forces exerted on the chassis as well as the spring. So because of this, we were able to narrow down the bolt to either aluminum or zinc-plated carbon steel. Zinc-plated carbon steel was chosen over the aluminum bolt because the steel part of the bolt is a lot stronger than the aluminum part. However, steel is very corrosive with aluminum. So to prevent this, we can zinc plate the bolt. Zinc is a lot less corrosive with aluminum, so adding the zinc plate will make it very less corrosive compared to steel. The bolt can also be painted to prevent the metals from touching. When the metals aren't touching, there is less of a chance for corrosion to occur. This adds another layer of protection against corrosion for the bolt and the chassis.
Comparison between aluminum 6061T6 and aluminum 6262T9. Both materials are within the list of material selection based on MPI calculation. 6061T6 has tensile yield strength of 276 megapascal, tensile ultimate strength of 310 megapascal. It is a high strength and weldable material. 6262T9 has the tensile yield strength of 380 megapascal, tensile ultimate strength of 400 megapascal. It has good machinability and high strength. 6262T9 was initially selected. It requires to go through T4 temporary, T6 temporary, T9 temporary, and code working. Cold working the 6262 alloy after age hardening is necessary in order to relieve internal stress, thus increase ductility. However, due to the natural shape of the tube, it's impossible to cold work after it has been age hardened. So we choose 6061T6 instead. It does not require cold working after age hardening, and it still has satisfactory properties. First, we will weld all of the parts into the frame. Then there are three main steps to heat treat a aluminum alloy. First, solution heat treatment. Second, quenching, and third, age hardening. First, solution heat treatment. To take advantage of the precipitation hardening reaction, it is necessary first to produce a solid solution. The process by which this is accomplished is called solution heat treating, and its objective is to take into solid solution the maximum practical amount of the soluble hardening elements into the alloy. The process consists of soaking the alloy at a temperature sufficiently high and for a time long enough to achieve a nearly homogeneous solid solution. For this particular 6061T6 alloy, we will be soaking this into the air furnace of the temperature 530 degrees Celsius, and the solution heat treatment time is 1 hour. Critical step in the sequence of the heat treating operation. The objective of quenching is to preserve the solid solution formed at a solution heat treating temperature by rapidly cooling to some lower temperature. This statement applies not only to the retaining solute atoms in a solution, but also to maintaining a certain minimum number of vacant lattice sites to assist in promoting the low temperature diffusion required for zone formation. For this alloy 6061T6, the quenching solution is room temperature water. We will be removing the frame from the air furnace and quickly transfer it into the water tank. The specimen is quenched until it reaches the room temperature. The water temperature is to be maintained under 38 degrees Celsius.
Coating and finishing processes can be performed on 6061 aluminum to improve its durability and corrosion resistance. These 6 processes include anodizing, mechanical treatments, powder coating, pretreatment, bright dipping, and liquid paint. Each process has its advantages and disadvantages and will be further explored in depth. Anodizing is a commonly used electrochemical process that plates a porous and corrosion-resistant layer of metal oxide onto the aluminum. This is achieved by immersing the metal in an electrolyte and applying a current to induce a controlled rate of oxidation that forms the metal oxide layer. Anodizing is used for bikes due to being in a high contact environment, often being bumped and scratched. The protective oxide layer is much more durable than other finishing processes, such as paint or powder coating. The downside of anodizing is that it may chemically interact with the surrounding environment due to the nature of the oxide layer. Various mechanical treatments that can be performed on the metal include buffing, blasting, polishing, grinding, and sanding. These treatment processes use various methods to all smooth out irregularities in the surface. The removal of irregularities is important, especially since the diameter of the tubes in the bike chassis are relatively small, and scratches can lead to the potential for pitting corrosion. Pretreatment using alkaline or acidic materials to etch or clean the metal can also increase its corrosion resistance by enhancing the adhesion of powder or paint. Pretreatment is commonly followed by a powder coating process. The use of pretreatment can also be used to enhance or modify the existing metal oxide layer. Powder coating involves the use of heat to force a solid resin solution to adhere to the metal and provide corrosion resistance. The advantage of using powder coating is the hardness and gloss that can be achieved due to the incorporation of the resin. When using powder coating, volatile organic compounds, or VOCs, are not emitted, which can be harmful for the environment. Bright dipping is another treatment method that can enhance the oxide layer using hot phosphoric and nitric acids. Paint coating, on the other hand, does emit VOCs, and the environmental impact should be taken into consideration. The paint coating is applied and then baked or cured to form a corrosion-resistant coating. Considering all finishing processes, liquid paint is the most reasonable due to its feasibility. The other methods, such as mechanical treatments or anodizing, may be difficult due to the shape of the chassis. One may argue that the tubes can be anodized prior to welding, but then the welding will not be reinforced and be a potential point of failure.